Hello, and welcome to the 11th lesson of the Big Data and Hadoop Administrator course, offered by Simplilearn. In this lesson, we will discuss the components or services in the Hadoop ecosystem. After completing this lesson, you will be able to list some of the services and open source components that work within the Hadoop ecosystem. List the advantages and key features of Hive. Describe the components of Hive briefly. Explain how to configure Hive in different modes. Explain the architecture of HBase and cite the advantages of using HBase. Explain the working of Apache Kafka. Describe the architecture of Apache Spark. Several services or open source components work within the Hadoop ecosystem. These include Apache Hive, HBase, Apache Kafka, and Apache Spark. In this topic, we will learn about Apache Hive, its features, and its components. Apache Hive is a data warehouse infrastructure built on top of Hadoop to provide data summarization, query, and analysis. It was initially developed by Facebook and subsequently developed by other organizations including Netflix, Nexar, High5, Last.fm, Scribd, Chitka, SassPulse, HubSpot, GrooveShark, and so on. Hive is a data warehouse software, and it facilitates structuring data, querying data, and managing large data sets residing on HDFS. It has several applications including machine learning and research development, social graph analysis, log data normalization, reporting and ad hoc queries, integral log processing and analysis, data mining and analysis, hosting fact and dimension data, user analytics, model building and trend detection, business intelligence and analysis. Some of the key features of Hive are: enables easy data extract, transform, load, or ETL with inbuilt tools. Supports structuring of multiple and varied data formats. Facilitates storage of file access directly in Apache HDFS or in other data storage systems such as Apache HBase. Provides query execution via MapReduce. Supports query execution using simple query language. Supports plugging in of custom mappers and reducers. Facilitates sophisticated analysis. Supports extension of query language with user-defined functions, or UDFs, user-defined aggregate functions, or UDFSs, and user-defined table functions, UDTFs. Permits read and write of data in non-Hive format. Effective with thrift, control-limited and specialized data formats. Effective for only batch jobs over large, append-only data sets, and cannot support online line transaction processing or OLTP workloads or real-time queries. Designed to support the scalability that Hadoop offers, and also to have loose coupling with input formats. Hive has 5 critical components. These are driver, compiler, shell, metastore, execution engine. The driver takes care of session handling, connectivity of Hive with Hadoop, and other relevant activities. To run queries on data in HDFS or in the local file system, Hive uses HiveQL, which has a syntax similar to that of SQL. It needs components to support the query functionality. The compiler is the component of Hive responsible for parsing queries, preparing query plans, and optimizing the plans. The execution engine then takes care of compiling queries and executing plans. The shell, or command line, is the component through which Hive can interact with data. Users can issue commands to query data, connect to external databases, change environment variables, or edit configuration properties. Metastore is the most critical component of Hive. It defines the mode in which Hive is set up. Metastore contains information about schema. Basically, the information includes metadata about data such as object definitions and how they are mapped to data which resides on HDFS or on a local file system. Later in this lesson, we will learn how Metastore governs the setup of Hive. Hive's Metastore can be accessed from other nodes through the Metastore service or from client nodes through the Hive Server 2 service, provided these services have been started and provide access to the Metastore. We learned that Metastore is the critical component of Hive. We will now learn how the Metastore governs the Hive setup in 3 modes. Embedded Metastore is the default configuration and works well for development and testing. In this configuration, the Metastore is stored locally in a Derby database and can be accessed by only one user at a time. Therefore, it enables only single-user access through the command line interface, or CLI. The data itself, however, can reside on HDFS or local machines. Local Metastore allows storing the Metastore in an external database such as MySQL, Oracle, and so on. The configuration also allows multiple users to connect to the same Metastore and work with objects. The data can reside on HDFS or local machine. However, multiple users can access the same Metastore and can thus access objects created by different users via different CLI. Remote Metastore allows access to other users to access the local Metastore. To do this, Metastore service is started on the machine which stores the Metastore. This data can reside on HDFS or a local machine. Adding Hive as a service, looking at configurations, and using command line interface or HUE to work with Hive. In this demo, you will learn how to add Hive as a service, look at the configurations, and use command line interface or HUE to work with Hive. Let's first look at how to add Hive as a service to the existing cluster. Click Actions and choose Add Service. Now, from the list of services, choose Hive and click Continue. In the Add Hive Service to Cluster 1 page, Cloudera Manager will show you the role assignments. The Gateway tab shows 4 machines on which the gateway can be set up for Hive. Now, click OK. The Hive Metastore Server tab will show on which machine the service will be stored. You can also choose a different machine with less load, as shown. Now, click OK. In the Web HCAT Server tab, you can choose the machine on which the service will be stored. Now, click OK. In the Hive Server 2 page, again, choose the machine for the service to get stored, and click OK. So, now you have assigned the host where the Hive-related roles will be running. Click Continue. Now to configure and test database connection, you have 2 options, which are Use Custom Databases or Use Embedded Database. In this case, let us use the default database that is the Use Embedded Database. Click Test Connection. Click Continue. The Review Changes page will show you which place Hive will store the data. We can also see the Metastore ports. Click Continue. Now you will see that the process has started for running the Hive service. Click Continue, and the Hive service is installed and configured on the cluster. Click Finish. As you've seen, Hive has been added to the cluster. Now, click the drop-down menu next to the Hive service and click Restart. so any services which are dependent on Hive will also restart. Click Hive service from the cluster. Now you will be able to see the status of Gateway Metastore Server, Hive Server 2, and Web HCAT Server. Click the Configuration tab, and that will take you to the page where you can give configuration details. Under the Scope configuration, you can give configurations which are related to Metastore Server, Hive Server 2, and Web HCAT Server. Under the Category configuration, you can see different categories in which you can change the settings. You can scroll down to see the different kinds of services configured which Hive depends on. So, for all the services that you have not set up configurations, such as Sentry, Yarn, and HBase, you will see None as default. Now click Cluster. Choose Cluster 1. And you can see Hive services running. If there is any kind of warning configuration issue, it throws a warning message. So, to check for the warning message, click as shown. The warning message shows 2 is less than the recommended minimum of 4. So if you are not sure, click Suppress. Now, enter the comments in the Comment section and click Confirm. Then click Close. Now to work with Hive, you should use Terminal. In the terminal, you can log in as root as shown. Then you can log in as HDFS, which is the default admin. Now you can type HDFS DFS-ls, and you can see what is there in your cluster. There are some directories. If you type HDFS DFS-ls/user, you can see the directory which is owned by Hive as a user and group. If you look in Hive as shown, you will see the warehouse directory where you will see some sample data. When you type Hive, it will take you to the command line interface, which allows you to work with Hive. Now, as you have logged into the Hive shell, you can start working on Hive. Type Show Databases, and this will show the different databases. Type set-v, and you can look at different properties, which are for environment variables, properties for MapReduce, properties for Hive, and properties for compression. Type set io.compression.codecs, which will show you the different compression codecs that are already available. To check the configuration of Hive, first exit from Hive by typing exit. Now type ls etc hive conf hive-site.xml, and you will see the auto-generated configuration properties for Hive. So, this is how Hive is added as a service. Now you can look at different configurations from command line interface. You can work on Hive by using web interface like Hue. You can also use Oozie to schedule workflows and submit the jobs. Now click on Actions. Click Add Service, and select Oozie from the list, and click Continue. To select the set of dependencies for the new Oozie, select the second option and click Continue. Now you will be able to see where the new Oozie server will run. Click Continue. Next, click Test Connection. Here, Oozie will use the default database, which will be created later. Click Continue. Now you will see where Oozie will store the workflow-related data and the data directory. Let's not make any changes and keep the default settings. Click Continue. So, you are adding Oozie as a service so that you can create workflows and submit jobs using Oozie. Now the Oozie server database will be installed. Also, some internal database tables and directories will be created, and the Oozie service will be started. After this, you can add Hue as a service so that you can use the graphic user interface of Hue to work with the cluster and Hive. Now click Continue, and you will be prompted to remove the services dependent on Hive. Click Cluster. Choose Cluster 1 and click Actions. Select Add a Service and select Hue from the options. Now click Continue. In the Customize Role Assignment for Hue page, you choose the machine where the Hue server should run. Now click Continue. In the Database Setup page, click Test Connection and click Continue. So now Hue service will be set up and Hue database will be created. Now you can use Hue as a service to work with Hive. Click Continue and click Finish. Once this is done, click Hue. Click Hue Web UI to log in to the Hue web interface. When you are setting up Hue for the first time, you will be asked for username and password. Here, you will provide Hue as username and password. After this, click Create Account. Now the Hue ID will be the Hue admin. Now, Check Configuration will check if all the configurations are right. Click Examples, and you will be able to see some examples. But if you click on the Examples, you will get an error message as shown, that the Hue user already exists. Since you have logged into Hue as a Hue user, you cannot delete that user. Click Query Editors. Click Hive. And this will show us to work with Hive from the graphic interface like you did from the command line interface. Now type Show Databases, and you can execute the query, and this will show you the output. So, in this demo, you have learned how to add Hive as a service, how to look at the configurations, and how to work with Hive using command line interface or Hue. Setting up Hive in different modes in Apache Hadoop cluster. This demo explains how to set up Hive in various modes in Apache Hadoop cluster. Before setting up Hive, you need to check whether all the daemons are active in both the machines D3 and D4, and ensure the Hive package is downloaded and installed on your machines. To check whether all the daemons are active in both the machines D3 and D4, perform the following steps. Open the machines D3 and D4. In machine D3, change the path to user local using the command cd/user/local. You can see the version of Hadoop using the command ls-all. Note that the Hadoop version used is Hadoop 2.6.4. Navigate to the Hadoop path using the command cd Hadoop. Start the storage-related daemons using the command sbin/start-dfs.sh. Note that the name node, data node, and secondary name node are started in the machines D3 and D4. Start the processing-related daemon, which is yarn, using the command sbin/start-yarn.sh. Note that the node manager is started for both the machines D3 and D4. Check the status of all Hadoop daemons using the command jps for the machines D3 and D4. Note that all daemons are active in both the machines. To download the Hive package, perform the following steps. You can download the Hive package from the link shown on the screen. Click the link, Archive of Public Software Releases. From the list of packages, click Hive and choose the required version. Here, let's select Hive 0.13.1 version. Download the tar file of this version. To install the Hive package, follow the given steps. Locate the downloaded Hive package in machine D3 using the command sudo ls-all/home/d3/downloads. Untar the hive.tar file in the user location using the command sudo tar-xvf/home/d3/downloads, followed by tar file. This creates the .bin file of Hive. Create a link to Apache Hive using the command sudo ln-s bin file name, followed by the link name. Here, the link name is Hive. Change the ownership to HD cluster for Hive and cluster. Change the directory to Hive using the command cd. Update the bash file in Apache Hadoop for cluster. To do this, use the command vi.bashrc. Note that the path for HBase, Scoop, and Hive are set. Update these paths in bashrc. The .bashrc is a shell script in which bash runs whenever it is started interactively. You can add any command in this file to set up the shell to use in your particular environment, or to customize your preferences. Open the Hive directory. You can see that the metastore_db is created. The Hive can be set up in Apache Hadoop in 3 different modes: embedded metastore, local metastore, and remote metastore. Embedded metastore is the default mode. In this mode, the metadata is stored locally. In local metastore mode, the metadata can be stored on the desired RDBMS. In remote metastore mode, the metadata can be stored on the local machine and can be accessed by Hive clients. Well, you have installed Hive successfully in your machine. Let's now look at how to set up Hive in embedded metastore mode. Remove the conflict file, if any. This can be done using the command rm-rf followed by the file name. In this demo, you can see there is a conflict file, so you must make your changes in hive-site.xml file. There are 4 properties for conflict file, and they are shown on the screen. Locate the default Hive conflict property. The configuration file for this property is shown on the screen. The file is provided only for documentation purpose, and any changes done to this file will be ignored. so you must make your changes in hive-site.xml file. You can search for important properties such as warehouse and javax.jdo to understand the place of metadata gets stored and the driver details. Look for file hive.rc. If not created, you can create this file. Some of the properties of hive.rc are shown on the screen. So, by default, the metadata is stored locally. Look for the databases using the command show database. You can create a sample database using the command create database. Here, let the name of the database be testdb1. By default, the created database is stored locally on the HDFS. You can create the table in the database using the command create table. Here, let the created sample table name be testtb1. However, we will use the existing metadata that is stored in local. You can access this file only locally. In machine D4, type the command bin/hive to locate the database. You can observe that the database created in the machine D3 cannot be accessed from machine D4. It shows only the databases available in this machine, D4. Thus, Hive is successfully set on the Hadoop on the embedded metastore mode. Let's now look at how to set up Hive in the local metastore mode. Set up an RDBMS in your Hive machine to simulate the real-time environment. To set up RDBMS, SQL, log in as root and use the command yum install MySQL-server. Start the MySQL daemon running the command service MySQL d start. To simulate a real-time environment, you need to create a user ID and password. To create an ID and a password, use the command /user/bin/MySQL_secure_installation. You can set the password here. You can remove anonymous users, disallow root login remotely, remove access to test databases, and reload privilege tables. The main goal of setting up MySQL is to store the metastore in RDBMS, and multiple users can access to it. You can see your created databases and tables using the command show databases and show tables respectively. You can also grant privileges to all the users with the command grant privileges on stat.star to root at username or host name or IP address identified by, followed by the password. Let the password be ABC123. Finally, specify the bind address. In the absence of bind address, Hive binds only the local host and can be accessed only by this machine. Here, only D4 machine can be accessed. You can specify the bind address using the command vi/etc/my.conflict. Let's now learn how Hive interacts with RDBMS MySQL. In machine D3, type the command ls/library to locate the library directory. You can see the jar file of MySQL. You can download this jar file from the link shown on the screen.
ये तो कह रहे थे राहुल कि ये मतलब कट रह जाएगा अपना ग्रीन हो जाता बंद हो जाता है
copy the downloaded MySQL connector file in Hive directory using the cp command. Ensure the hive-site.xml file is present in the machine D3. This file informs the machine to follow the properties mentioned in it. Similarly, perform the steps in machine D4. Now, the two machines, D3 and D4, that have the same Hive installed point to the same location where the metastore is to be stored. So now, multiple users can work with Hive, can create tables, and store data. Thus, Hive is successfully set on the Hadoop and local metastore mode. Let's now look at how to set up Hive Hadoop in remote metastore mode. In remote metastore mode, the metadata can be stored on the local machine and can be accessed by Hive clients. In machine D3, change the directory to conflict and locate the hive-site.xml file using the command vi. Remove the javax.jdo properties from the hive-site.xml file. This enables the metastore data to store locally on the machines. Note that only the default properties are available. The database, India, is created and stored locally. To make this database that is stored locally accessible by various machines, use Metastore service. To get Metastore service, log in as HD user and navigate to the bin file of user local Hive. Type the command bin/hive-service help to see the services offered by Hive. Run the Metastore service. To run the Metastore service, use the command bin/hive-service metastore. This allows Hive to be accessed by various users. Ensure you log out from the Hive while you run the Metastore service. Similarly, perform the steps in the machine D4. To connect to the Metastore database, India, stored in the machine D3 from machine D4, delete the javax.jdo properties and add a new property that links the stored Metastore database in machine D3. The new property added is hive.metastore.uris. Provide the value for this property. The value of the hive.metastore.uris is thrift:/d3:9083. Log into the Hive in machine D4 and type the command shown, bin/hive. You can now access the database stored in machine 3 from machine 4. Thus, Hive is successfully set on Hadoop on remote Metastore mode. This concludes the demo on how to set up Hive in various modes in Apache Hadoop cluster. Looking at Hive configurations and making changes. In this demo, let's look at Hive configurations and how to make changes to Hive. In the cluster, which is cluster 1, Hive is already added as a service. Now, click Hive, and you will be able to look at the instances and the configuration details. Under the Status tab, you can see that Hive Metastore Server is running. You can also look at the details of Hive Server 2, Web HCAT Server, and Hosts. If you click Instances, you can see details about different roles which are running on different machines and the status of roles. That is, if the roles have just started or if they are running already. Now, click Configurations, and you will be able to see configuration properties which are used for Hive. In Configurations, you can filter the configurations based on different properties. Now, let us look at the different properties under Configuration tab. On clicking Hive Service-Wide, you will be able to see where the metadata is getting stored, and if Hive is going to use Zookeeper and Yarn or not. In Hive Reduced Tasks property, you will see how many reduced tasks will be run by Hive. Also, in Hive Bytes per Reducer, you can increase or decrease the data as required. The Hive Max Reducers option will give information on the maximum number of reducers that Hive can execute. You can click Undo button to revert any changes if required. When you click the question mark icon, it gives information about what this property change can do. When you make any changes to the configuration properties, Save Changes will be highlighted. You can also add specific properties using the configuration snippets. In the Configuration page, click To go to the next page of configuration properties, such as different ports, different settings where the Metastore database will be stored, the Metastore database type being used, and so on. Now click Scope on the left-hand corner and look under different properties under Scope. Click Hive Server 2 and you can see different properties under it, such as heap size, information about Apache Spark, and so on. Now click Web HCat Server, where you can see all the properties related to that. Under the Category tab, you can see different properties like Advanced, Logs, Monitoring, Performance, Ports and Addresses, Resource Management, and so on. When you click Ports and Addresses, it will show which port Web HCat will use. Once all the changes are done, click Cluster, and then click Cluster 1. Under Services, if you see Restart icon highlighted, you will have to restart those particular services. For this, click Actions and select Restart from the options to restart all the services at the cluster level. For stale configurations related to client, click Stale Configurations, which shows what changes have been made. Now click Restart Stale Services. In this demo, you have seen how to look into the configurations and how to make changes to Hive. HBase. What is it? HBase is another service in the Hadoop ecosystem, and it is also called as Hadoop's database. Let us learn more about it. Other features of HBase are: it is not a relational database. It does not support SQL. It cannot enforce relationships. It does not support transactions between rows. It does not require custom-made or expensive disk configurations. It does not require a huge RAM, and it does not need the RAM on a single machine. Before we delve into the details of HBase architecture and its implementation, let us discuss the need for HBase. One of the drawbacks of using a relational database system is that a storage system is required in the backend to provide a persistent layer for the application server in the front end. This works well when there are a limited number of records. However, when a large amount of data is retained, the architecture of the common database systems tend to show weaknesses or incapabilities. Some of the tasks that prove challenging with huge data are normalizing and indexing data, implementing joins, executing stored procedures, using transactions to ensure data consistency and referential integrity, using a domain-specific language like SQL. While handling these tasks for a large number of records, if the number of users or threads increases, it increases the pressure on shared database servers. The CPU and I/O load also increases, and any further growth of the database may become difficult to handle. These challenges can be solved in any of the following ways. Add slave database servers to handle the pressure and ensure that the slave servers are efficient as the master servers. Set up a single master server that supports fewer writes but handles large number of reads. Add a cache that stores reads in a very fast in-memory system. Scale the master server vertically, which is a rather costly option. Denormalize schemas. Avoid use of built-in features like stored procedures. Store only the amount of data that can enable optimization of access patterns. Determine the costliest queries and pre-materialize them to plan their implementation. If there is a further increase in the workload, then sharding can be viewed as a solution. However, it is costly and rather difficult to operate. So, when implementing a new product, opt for a robust solution that can cater to the needs of the business or use case. One should evaluate the considered solution in certain dimensions to classify its strengths. Some of these dimensions are the data model, the storage model, the consistency model, the physical model, the read-write performance, failure handling, use of secondary indices, compression handling, load balancing, handling locks, waits, and deadlocks, handling atomic read, modify, write. Then, based on the evaluation and the requirement of the business or use case, select the best solution. Over the years, while solving internal data problems, several companies came up with different solutions, and so, today, there are more than 225 non-relational database systems, or NoSQL databases, that exist in the market. Not only SQL was a popular term coined by Eric Evans for these databases, and conveys the essence of these databases, which is, they support languages other than SQL. Some of the companies that developed NoSQL databases are shown on the screen. HBase is used to capture incremental data from various sources such as web crawls, advertisement impressions, time series generated from recording metrics, capture user interaction data such as metrics on site activity, metrics captured from monitoring the product, metrics on user interactions with the product, number of likes or clicks on a site, capture raw clickstream and telemetry and user interaction data incrementally and process it using different processing mechanisms, back applications on which users consume or generate large amounts of content, such as Twitter, Facebook, Instagram, and other microblogs. HBase is created using Java and is built on top of Hadoop and Zookeeper. It is a database, also called Hadoop database, and it provides random access, which means that one can read from and write to the database in a random manner. Following are some of its features. Stores structured, semi-structured, and unstructured data. Stores tweets, parsed log files, product catalogs, customer reviews, videos, and images. Stores integers in one row and strings in another row of the same column. That is, it has a column-oriented data storage mechanism. Runs on a cluster of nodes. Is flexible and scalable. Provides a key-based access to a cell or a range of cells. Replicates data and thus protects data from loss due to cluster node failure. Guarantees high availability by using standby master nodes. provides record-level consistency. Provides atomicity, consistency, isolation and durability, or acid-level semantics for each row of data. Is capable of filtering and has better scanning throughput. Supports coprocessors. Facilitates random write actions. Optimizes read actions. HBase can be considered the database solution in any of the following scenarios. There is an existing Hadoop cluster. The volume of data is huge. There is a need for faster and random read-write actions. The data access patterns are well known in advance. HBase also uses Java API, and HBase tables can be used as input to MapReduce jobs as well as to Hive and Pig tasks. HBase can also be implemented in a Lambda architecture that combines real-time analytics with batch processing. HBase installation is complicated compared to an RDBMS installation on a single server. Because it is installed on clusters that comprise servers anywhere between a dozen to 1,000 or more. Thus, it is a distributed NoSQL database. Distributed computing often encounters issues with respect to the following: remote process coordination and management, locking of nodes, distribution of data, network latency. HBase integrates with other technologies, such as Apache Hadoop and Apache Zookeeper, and leverages their features to solve these problems. Let us learn about the architecture of HBase. The following three layers comprise the HBase architecture, as illustrated by the image on screen. HBase Master, Region Servers, Zookeeper. The HBase Master performs the following tasks. Coordinates with slave nodes, which are usually region servers that are co-located with data nodes. Handles DDL operations, such as creation and deletion of tables. Handles creation and deletion of regions as well as assignment of regions on startup or during recovery. Monitors all slaves or region servers for notifications from Zookeeper and other admin functions. Zookeeper maintains the cluster state constantly. The region servers manage the data that can be read or edited. Clients communicate directly with region servers to access data which resides on Hadoop data nodes. HBase tables are divided into regions based on a range of row keys. A region has a start key and an end key, and all the rows in the tables that fall in that key range make up the region. A set of regions is assigned to a region server. A region server can serve or handle about 1,000 regions. The Zookeeper keeps track of the status of the servers in the cluster. It maintains information about which servers are in live status and available, and sends out notifications in the cluster when any of the servers fail. It ensures a common shared state of servers by constantly checking and obtaining consensus. HBase uses Zookeeper as a distributed coordination service and obtains information about the status of servers. Region servers and the active HMaster connect with Zookeeper through a session. Zookeeper also keeps track of ephemeral nodes for active sessions via heartbeats. Java client APIs, as well as external APIs, can connect to HBase and access its data. External APIs connect to HBase through interfaces such as Thrift, Avro, and REST. Let us learn some more about region servers. The image on the screen helps understand the various components of region servers. A region server runs on an HDFS data node. Its components are write-ahead log, or WAL. Write-ahead log is a file on the distributed file system that is used to store new data that is yet to be written on the disk. In case of a failure, this file helps to recover the data. Block cache. This component stores frequently read data. It functions as the cache for read actions. When it is full, the least recently used data is removed. Memstore. This component acts as the cache for write actions. It sorts the data before committing it to the disk. Each column family in each region has one memstore. H-files. This component stores the rows as sorted key values on disk. Coming to the actual reading and writing tasks in HBase, there is a special HBase catalog table called the meta table. This table stores the location of all regions in the cluster. The meta table has a B-tree structure and comprises the key, which contains the region start key, and the region ID values, which contains the region server. Zookeeper stores the location of the meta table. When a client has to read or write data to HBase, it uses Zookeeper and accesses the region server that is hosting the meta table. The client queries .meta.server to get the region server corresponding to the row key it wants to access. The client caches this information along with the meta table location. It then obtains the row from the corresponding region server. For read actions that take place thereafter, the client uses the cache, retrieves the meta table location using the previously passed row keys. HBase setup can be in any of the following modes: standalone, pseudo-distributed, fully distributed. Adding services such as HBase, Impala to CDH cluster, and looking for specific information. In this demo, you will learn how to add other services like Pig, Impala, HBase, and so on in Hadoop cluster. First, click Actions, then on Add a Service. You will find a list of services. Choose Impala and click Continue. You will be asked to customize role assignments for Impala, where you have Impala Catalog Server, Impala State Store, and Impala Daemon. When you click on Impala Catalog Server, the host name will be 147 by default. Select 149 to reduce some of the load on the first machine, and click OK. On Impala State Store 2, the host name will be 147 by default. Select 149 and click OK. Under Impala Daemon, select All Hosts. Click Continue. Under Impala Daemon Scratch Directory, you can find the place where the Impala stores data. Click Continue. Once you click Continue, Impala User Directory will get created, and the Impala service will be set up. During the time it takes to set up, you can check for the role logs and the commands which you have issued. Once the setting up is done, click Continue, and then click Finish. In Cluster, restart the services, wherever required, by clicking Restart Stale Services and redeploy client configuration. Note that Impala stores metadata in the metastore, which is also used by Hive. By using this method, Impala can benefit from the features that are available to Hive. Also note that whenever you are restarting a service, other services might be linked to it. Restart the other services as well if required. At any point of time, you can abort the restarting process, and you can either restart only the required services or perform a restart on all services. Once the restarting is done, click Finish and you will be taken back to Cloudera Manager. If you see any health issues, click Cloudera Manager below Cloudera Manager Service to check the health issue details. Click the arrow on the right and click Restart. Once it restarts, click Actions and select Add a Service to add another service to the cluster. Select HBase, which is a NoSQL database and used to store unstructured data and allows faster random access and real-time access to data, and click Continue. select Master, which is a master for HBase cluster. Now select 149 as hostname to reduce the load on one machine and click OK. For HBase REST server, place it on the fourth machine with host name 197 and click OK. The HBase Thrift server acts as an interface to use HBase. So place the Thrift server on fourth machine, for which the host name is 197, and click OK. For Region server, select All Hosts and click Continue. You will see the location where the HBase stores its data by default. Once you click on Continue, the root directory will be created, and you can also find the role log along with the commands that are issued. Click Continue and then click Finish. If you find any restart services, click on the icon and then click Restart Stale Services. And under Review Changes, disable Rolling Restart and check Redeploy Client Configuration. Once the service gets restarted, click Finish. Once you click Finish, the cluster will be loaded with HBase. Under Status, you can see all the servers running. Click Instances to find out what hosts the servers are running. Click Configuration to get the configuration for HBase, like the data storage path and port number. On the left, you will see a column, Scope, where you can find the details of each server. Under Actions, you have Enter Maintenance Mode, Create Root Directory, Deploy Client Configuration, and so on. Click HBase Web UI. It will take you to the web user interface, which has all the information about region servers. If you are looking for more information on region servers, click Memory, Requests, Store Files, and Compactions. Click on a region server and you will be taken to the machine where the region server is stored. This can be done only using a public IP address. Click Quick Links, and it will display these options. Using these links, you can view the details of a region server. Table Browser will have the list of all tables under HBase. Table Statistics will have the information of tables, like table size, get operations, write operations, and so on. In Clusters, click Impala. Under Configuration, you can see the information based on scope and category. Click Queries to check if there are any queries related to Impala. On the left, we have Workload Summary, which has all the details related to the duration, memory used, number of HDFS files that were read, and so on. If you know the query, type it in the search bar. In Web UI, there are two options. One is Impala State Store, and the other is Impala Catalog Server. Click Impala Catalog Server. You will get the information about the version, hardware, and operating system related to process, which will be helpful while performing and monitoring a service. In Quick Links tab, you have Alerts, Critical, and All. We have Start, Stop, Restart, Add Role Instances, Rename, Enter Maintenance Mode, and Create Impala User Directory in the Actions tab. Click Commands to find out all the commands that were given related to Impala. In Apache, you have to manually perform the configuration, but in Cloudera Manager it is easy to add, remove, or change services. This brings us to the end of the demo on adding a service like HBase, Impala, to Hadoop cluster and editing the configuration files under each service. In this topic, we will learn about Apache Kafka, another service in the Hadoop ecosystem. Kafka is a fast, scalable, and durable distributed messaging system. It follows the publish-scribe messaging pattern. Kafka is also a partitioned, replicated, commit log service. Although Kafka essentially functions as a messaging service, its design is unique. Many companies use Apache Kafka. Some of them are LinkedIn. LinkedIn uses Apache Kafka to stream activity data and to obtain operational metrics. The LinkedIn newsfeed is powered by Kafka. Yahoo. Many teams in Yahoo use Kafka, including the media analytics team, which uses it for real-time analytics. A web-based tool called Kafka Manager helps maintain Kafka clusters. This interface helps to identify topics which are unevenly distributed across the cluster. Identify topics that have partition leaders unevenly distributed across the cluster. Manage multiple clusters. Select the required replicas. Reassign replicas, and create topics. Obtain an overview of the cluster. Twitter. Kafka powers the storm stream processing infrastructure at Twitter. Netflix. Kafka handles the real-time monitoring and processing of events at Netflix. Square. At Square, Kafka acts as a bus and moves system events through various data centers, including metrics, logs, custom events, and so on. Mozilla. Kafka is used to obtain performance and usage data from the end user's browser to be used in projects like telemetry, test pilot, and so on. Kafka categorizes feed of messages into topics. Messages are published to topics. There are processes that publish the messages to a Kafka topic. These are called producers. Producers are often web servers or mobile applications. The messages they send might be log information, such as which user clicked which link at what time. Certain processes subscribe to topics and process the feed of published messages. These are called consumers. The consumers use the information to generate analytics, monitor for unusual activity, or generate recommendations for users. Kafka is run as a cluster of one or more servers. Each server in a Kafka cluster is called a broker. Observe the images on the screen to see how Kafka works in a real-time scenario and a technical view of the working of Kafka. The Kafka cluster maintains a partitioned log for each topic. Observe the image on the screen that illustrates how each topic is structured. Each partition is like a commit log. Messages are continuously appended to it. Thus, a partition contains an ordered sequence of messages that do not change over time. Messages in the partition are sequentially assigned unique identification numbers called the offsets. In order to ensure durability of data and avoid data loss due to machine failures, each partition is stored on a disk and is replicated across multiple machines. Note that Kafka only appends messages to the end of a partition. It only writes the message at the end of the log, and it cannot facilitate modification of previous messages. Note that in this case, logs mean any kind of append-only file with ordered records. Advantages of the partitions are: the log can scale to a size that is beyond a single server's capacity. A topic can have many partitions so that it can handle any amount of data, although each individual partition needs to be of a size that does not exceed the capacity of its host server. They work in parallel as a single unit. Observe the image on the screen to see the illustration of Kafka topics, producers, and consumers. Messages are nothing but byte arrays. They can store an object in any format, such as string, JSON, Avro, and so on. If a message is identified by a key, the producer ensures that messages with the same key are sent to the same partition. A consumer group is created when multiple consumers want to read messages from a topic. Each consumer in the group reads messages from a subset of partitions that belong to a topic. Each message in the topic is delivered to one consumer in the consumer group. Messages that are identified by the same key are sent to the same consumer. Distribution of partitions is done in Kafka as follows. Servers across the Kafka cluster handle the partitions of logs. Each server handles data and requests for a group of partitions. To enable fault tolerance, each partition is replicated across multiple servers. For every partition, one server acts as the leader and one or more servers act as followers. All read and write requests to the partition are handled by the leader. The followers simply replicate the leader. Suppose the leader fails. One of the followers takes over as the new leader. In order to balance the load, each server acts as the leader for some partitions and as a follower for other partitions. Kafka has some unique features. Treats topic partition logs. Retains unread messages rather than tracking which consumer reads which message. Supports a large number of consumers. Retains large amount of data with negligible overhead. Kafka is different from other message brokers because it is structured as a log. Data streams in Kafka are structured as partitions, and each partition is a log. Partitions are independent of each other, are handled independently on different servers, and thus facilitate scalability of Kafka. Structuring as a log is a major advantage because using logs is the best solution as seen in databases, and this ensures reliability of data storage, synchronization with a replica, consensus in a distributed algorithm such as Raft, recording of activity data, robustness of data infrastructure when scaled. Thus, by using logs, many issues faced in achieving reliability, scalability, and maintainability of large-scale data systems are overcome. Let us now see some of the Kafka use cases. Messaging. Compared to traditional messaging systems, Kafka has better throughput and built-in partitions to handle replication and achieve better fault tolerance. Therefore, it is a good solution for large-scale message processing applications, better than traditional message brokers. Website activity tracking. Originally, Kafka was developed to rebuild user activities as real-time publish-subscribe feeds. Site activity such as page views, searches, likes, and so on are published separate topics for each activity. These are available for real-time processing, real-time monitoring, offline data warehousing systems, and reporting. Thus, Kafka is a good solution since activity tracking generates high volumes of data, since larger number of activity messages are generated for page views, for real-time processes, for dashboard activities, and offline analytics in Hadoop. Metrics. Kafka is a good solution for monitoring of operational data. Statistics from distributed applications are collected and centralized feeds of operational data are generated. Event sourcing. Since Kafka supports storage of huge amounts of log data, it is a great solution as the backend for an event sourcing style of application that logs state changes as a time-ordered sequence of records. Log aggregation. Kafka sometimes replaces a log aggregation solution. Log aggregation solutions collect physical log files from servers and place them in a central server for processing. Kafka abstracts the file details and provides the log or event data as a stream of messages. This helps to achieve lower latency processing, support multiple data sources, and provision distributed data consumption. Kafka performs well and ensures stronger durability as compared to log-centric systems such as Scribe or Flume. Stream processing. Sometimes data is processed in stages. raw data is consumed from topics and then transformed into new Kafka topics to be used by applications. For example, an article recommendation may crawl content from RSS feeds and publish to an article's topic, which is further processed, transformed, and published to another topic. This data may be processed again and published to another topic, and so on. Popular frameworks that implement such transformations are Storm and Samza. Commit log. Kafka has the log compaction feature that enables it to serve as an external commit log for a distributed system. The log supports replication of data between nodes and resynchronizes failed nodes to restore data. In this topic, we will learn about Apache Spark and its architecture. Apache Spark is an engine for large-scale data processing. It is an important product from the Apache Software Foundation. Its features are: it provides fast, simple solutions for existing development environments and storage systems. It integrates easily with existing applications. It supports programming languages such as Java, Python, Scala, SQL, and R. It runs on clusters that are often used for Hadoop jobs. The resource manager of Hadoop Yarn manages the Hadoop cluster and Spark. It can also run on clusters managed by Apache Mesos and can be managed by other resource managers. Amazon Web Services EC2 or Elastic Compute Cloud can easily launch Spark. In addition to integrating with HDFS, Spark integrates with data storage systems such as MapR, Google Cloud, Amazon S3, Apache HBase, Hive, and so on. Spark can cache datasets in memory, thereby speeding up iterative data processing, such as those implemented in machine learning algorithms. Spark APIs enable streaming, machine learning, or working with SQL workloads that require fast and iterative access to datasets. Applications that can leverage Spark features can be created with Spark running on Yarn. These applications obtain information using a single shared dataset on Hadoop. Apache Spark consists of the Spark core and a set of libraries. The core is a distributed execution engine. Java, Scala, and Python APIs provide a platform for distributed ETL application development. Some of the organizations using Spark are ActNow. Now Apps is a big data, real-time, predictive analytics platform, is powered by Spark. The company uses Spark SQL, MLlib, and GraphX components for both batch ETLs and analytics on telecommunication data to quickly extract meaningful information. Arimo uses Spark with Hadoop to obtain visual, real-time, predictive analytics. Support is also built in for R, Python, SQL, and natural language. eBay uses Spark Core to collect log transaction information and to generate analytics. OpenTable uses Apache Spark for processing logs and for ETL. The recommender system, powered by Spark MLlib matrix factorization, uses the data obtained. Spark streaming for real-time analytics is also being considered. Kelku uses Spark Core, SQL, and streaming for product recommendations. BI and analytics, filtering real-time malicious activities, and data mining. The Spark stack consists of the Spark core and a set of libraries that are optimized and can provide solutions for specific use cases. The Spark core is the heart of Spark and handles management functions such as task scheduling. It depends on a programming abstraction called Resilient Distributed Datasets, or RDDs. The image on screen illustrates the Spark architecture, showing the core and the libraries. The Spark libraries or modules are Spark SQL, works with structured data and supports executing SQL queries and generating complicated algorithm-based analytics. It facilitates integration with existing databases and data warehousing by supporting Hive, JDBC, ODBC connections. Spark Streaming is the module that processes streaming data such that it is fault-tolerant and scalable. It provisions easy integration with sources of data streams like Flume and Kafka. Flume is optimized for data logs, and Kafka is optimized for distributed messaging. Using RDDs, Spark Streaming can repurpose streaming applications so that archived data may be analyzed. MLlib is the library of Spark that can implement statistical and commonly used machine learning algorithms. Some of the algorithms are hypothesis testing, regression analysis, classification, clustering, and principal component analysis. GraphX is the module that works on tasks concerning analysis and computation of graphs and data and supports an API for graph processing. It includes several popular graph algorithms, such as PageRank. Spark R is the module that supports using the language R over Spark. DataFrame API is a new API that supports scaling of data from kilobytes to petabytes, various data formats and storage systems, integration with other big data tools, optimization of queries using the Spark SQL Catalyst Optimizer. Spark jobs are capable of performing multiple operations consecutively in memory. The operations are performed on disk only when there is a limitation on the memory. The processes are all different from one another, and Spark provides an integrated data pipeline that is easy to manage. Resilient Distributed Datasets, or RDDs, is a concept that facilitates in-memory storage of data distributed across a cluster. It ensures fault tolerance by tracking the lineage of transformations applied to data, efficiency by parallelizing data processing across multiple nodes, and also by minimizing data replication between those nodes. The following types of operations can be carried out on data in an RDD. Transformations, which create a new RDD by transforming the data in the original one by executing processes such as filtering, mapping, and so on. Actions, such as using count function, which measure but do not change the original data. When using RDDs, the original RDD remains unchanged throughout. The transformations from the first to the last RDD are logged. They can be repeated if there is data loss or a node in the cluster fails. Transformations are executed only when an action is invoked. This improves performance. It also avoids bottlenecks that arise when applications are stalled because another process has to conclude. RDDs are mostly stored in memory, thereby increasing the performance of the cluster. This is particularly advantageous for iterative queries or processes. Hadoop and Spark work by providing some functionalities to each other. Spark depends on open-source implementations, such as Hadoop, for persisting data, recovering from disasters, and managing clusters. This is because it does not have the capacity to deal with management and administration tasks of data processing and analysis. Spark is a good supporting component in the Hadoop cluster deployment, and Hadoop provides Spark with the following features to achieve the tasks it cannot perform. Yarn Resource Manager, to handle the responsibility of task scheduling across nodes. HDFS, to handle data storage when a cluster reaches its memory limitations, or when Spark is not running. Disaster Recovery, by cluster replication and data mirroring across clusters. Data security handling through security implementations in Apache Hadoop or other open-source implementations like Nox or Ranger. Distributed Data Platform, to deploy Spark jobs on a distributed cluster. Spark supports Hadoop in the following ways: contributing to Hadoop-based jobs through Yarn, adding to the capabilities of a Hadoop cluster by rapid in-memory processing of large data volumes, providing SQL, streaming, and graph processing capability to Hadoop.